So here's a new video for 7A. The beginning for our next exam. We'll be starting with 7A and going into chapter 8 and 9, I believe. So fundamentals of probability is basically now we're going to actually find ways to calculate saying, the probability of this occurring or the probability of this occurring. In chapter 6, we discussed a little bit about basically distributions and, probabilities of that nature with normal distribution or the empirical rule and z-scores. So let's move on to fundamentals of probability, 7A. So as always, let's start off with a few definitions. Outcomes are the most basic possible results of your observations or experiments. For example, if you toss two coins, one possible outcome is heads or heads and tails, or you could also get tails then heads. You could also get tails, tails, or you could also get heads, heads. These are just two possible outcomes. An event consists of one or more outcomes that share a property of interest. For example, if you toss two coins and count the number of heads, the outcome heads, tails, and tails, heads both represent the same event of one heads and one tail. Okay, so the event is kind of I don't want to say the process, but the almost like the experiment or the fact that we're tossing two coins, that is the event, and the outcomes are more like what could happen. These are the different scenarios that could happen. So hopefully that makes it kind of clear what the difference between event and outcomes is. Okay, so let's take a look at a problem like this. So it says, consider families with two children. List all of the possible outcomes for the birth order of boys and girls. Okay, if we are only interested in the total number of boys in the family, what are the possible events? Okay, so we're going to let B represent number of boys and G represent number of girls. Okay, so there are four different possible birth orders or outcomes. Okay, so outcomes. Okay, so we could have, first thing that could happen, there could be a boy and then another boy born. There could be a boy and then, there could be a boy and a girl born. There could be a girl and a boy born, or there could be a girl and a girl born. Okay. By the way, one way you can kind of determine how many possible outcomes there are going to be, or sometimes this is referred to as your sample space of this event. So the sample space for this event is boy, 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 girl, girl, boy, or girl, girl. Basically, what you do is you think of how many different possibilities there are. So it could be boy, it could be girl, right? So there's two outcomes, all right? And then how many times did you perform this situation, or how many of this event took place? So you chose two children, okay? So it's 2 squared. What if we had boy or girl, and we wanted to have how many different outcomes could happen with 3 childbirths? So we would say 2 cubed. So there's 8, 2 squared. So there's 4. So in this case, we're using the 4 right here. So I kind of know that I have everything because there's 2 children being born and there's 2 outcomes for each different childbirth. Okay. So these are our 4 different possible birth orders or outcomes: is boy, 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 girl, girl, boy, girl, girl. And there are 4 of them. Okay. Let's see here. All right. So, by the way, what if it was, just to kind of reiterate the point before I move on, I just want to be sure. What if there was a 6-sided dice? So suppose 2 fair 6-sided dice are rolled. How many possible outcomes Okay. Well, or I should say, how many possible. See, the way your book describes outcomes is a little bit different than in my statistics class. I just want to make sure I'm keeping up with their definition. For example, if you toss two coins, one possible outcome is heads, tails, and another possible outcome. Yeah, okay, so they're still doing it the same as me. So are rolled, how many possible outcomes are there? Okay, well, when you roll a six-sided dice, there's six choices, right? You could have a 1, a 2, a 3, a 4, a 5, and a 6. And how many dice are you rolling? Two of them, so it's 6 squared. So there would be 36. That's just, I just kind of wanted to reiterate, that's how you can find the size of the sample space or the number of outcomes. Okay. So this is very, very vague. I just wanted to show you what your book shows. In a pure statistics course, they would actually say, in general, anything that has less than a 5% chance of occurring, 5% or less of occurring is considered unlikely, and anything that is, more than 95% is likely. But that's fine. So in this course, they say the probability of an event expressed as P. So, you could say probability of event A occurring, right? That's how you write it. Is always between 0 and 1 inclusive. So no event can, ever be more than 1 or a more than 100% likely. And it can never be negative. It can never be less than 0% likely. So everything is between 0 and 1 in terms of probability. Okay. The probability of 0 means the event is impossible, and the probability of 1 means the event is certain. And you can also think of 1 as 100%, right? Like it's 100% certain. So they say right here, this is a 50-50 chance, and anything between above 50-50 is considered likely. That seems a little bit vague. And then unlikely. So this is how your book thinks of it. Again, if you take a statistics course, they'll go a little bit more in depth, but we're not taking a pure statistics course. So we're going to be okay with that. So anything more than 50% is considered likely, and anything less than 50% is considered unlikely. But that's a very loose terminology or loose wording that we're using in this course. Okay. Theoretical method for equally likely outcomes. So you count the total number of possible outcomes. Then among all the possible outcomes, count the number of ways the event of interest A can occur. So basically, a lot of times they call this a success. They say the thing that you're worried about, whatever event you're worried about, you call that event A, that would be your success. So, and don't think of success as a good thing or a bad thing. Don't carry that connotation with it. Just think of success as what you were looking for versus what there is total. Okay. And then it says determine the probability of A. So here's the formula they give us. The number of ways A can occur divided by the total number of outcomes. So that's why I wanted to kind of reiterate to you guys up here that this is how you can find the total number of outcomes or the sample space easily. Okay, so this formula is the probability of event A, and this is our theoretical method for equally likely outcomes. Okay, so coins and dice, we like to use these in statistics courses as well because they're kind of set. And a lot of people, everybody knows what a coin looks like, and a lot of people know what dice look like. And in fact, there's, whole cities are built on gambling based on dice. So it's very common to use coins, dice, and also playing cards are three of the main ways people try to explain probability, just because they're, everyday items that we can see. So it says apply a theoretical method to find the probability of exactly one head when you toss two coins. Okay, so we're going to go back here. I guess we won't go back. We'll keep it right here. I normally delete the solutions, but I really like their pictures that they had, so I didn't want to get rid of them. So if you notice right here, what they're doing is they're giving us all the outcomes, right? And the event is 0 heads, 1 head, 1 head, or 2 heads. So we're concerned, okay, with what? Exactly one head being flipped on your coin, okay? So the probability of only 1 heads, okay? Now, what will that equal? So how many of these situations have only 1 heads? Well, we have this one here. Oops, that's not a really good looking one. Let's use this. So this one here has 1 heads, And then this one here has one head. Okay. Now we won't count this one because that has two heads, and we won't count this one because that has a 0. Okay. So what we're going to do is we're going to say, well, there are two scenarios where we get one head, and that could be the first coin was tails, and then the second coin was heads, or so that would be this, or the first flip was heads, and then the second coin was tails. But in both situations, we got one heads, right? Or one head. So we take the number of ways A can occur. So we found out it's 2, and then we divide it by the total number of outcomes. Well, there are 4, 1, 2, 3, 4 outcomes. So 2 out of 4 is 1/2. Or most of the time they like to use decimals, I think, when you're using calculator. I personally prefer 1/2, but just read the question and see how they ask it in the homework and on the quizzes and stuff. Okay, so we have this next one here. And again, they tell you that we get 1/2. Now this next one says getting a 3 when you roll a 6-sided dice. Well, how many ways can you get 3? Just that one way. So there is probability of a 3 on a 6-sided die. Okay. Now that means that we're going to get probability of 1 out of 6 because there are 6 outcomes and only one of those outcomes is a 3. All right. So it says playing card probabilities. All right. Now this is a big one because in playing cards, again, not everybody plays cards. I still remember as a kid, I played cards all the time with my grandfather. So I've been playing poker and blackjack since I was probably like 7, maybe even earlier. That was like a big game. We would play cards, we would play chess, checkers, you name it, any card game we would play as well. But in cards, there are 52 playing cards in a standard deck. So this will kind of explain it to you, those of you that don't play a lot of cards. They are known as 4 suits: hearts, spades, diamonds, and clubs. Okay, so we have hearts, spades, diamonds, and clubs. Okay, now hearts are red, spades are black, diamonds are red, and clubs are black. Okay, so these are the 4 suits. 2 of them are red, 2 of them are black, and you have hearts, spades, diamonds, and clubs. Each suit has cards for the number 2 through 10, plus a jack, queen, king, and an ace. So each suit has 13 cards, and there are 4 suits. So there are 52 cards in a deck. Okay, so that's where they got the 52 from. All right, and then it says hearts and diamonds are red, and then spades and clubs are black. If you draw one card at random from a standard deck, what is the probability that it is a spade? Okay, so I'm going to write probability of a spade. Okay, so we have to think, well, how many spades are in the deck? Well, we just said there are 13 cards in each suit. So 13 of them would be a success, or 13 of them would be the event we're looking for. Now, how many total cards are in the deck? 52. So this would become 1/4. Okay, or 0.25. All right. So it's pretty straightforward. And again, we're not going to get too crazy into statistics. That's just one thing. Now, the thing is they could get fancier. So we could come over here and we could say, find the probability of getting a red jack. Okay, so probability of red jack. Now we have to think, how many red jacks are there? Well, there's 4 of every single card in the deck, and every card has 2 red cards and every card has 2 black cards. So the number 5, for example, there's 2 reds that are 5, or 2 5s that are red, and there's 2 5s that are black. Okay, so the probability of getting a red jack would be 2, right? Because there's only 2 jacks, there's 4 jacks total, and 2 of them are red and 2 of them are black. So 2 out of 52, which would be 1 out of 26. Now, what if I said probability of getting a face card? Okay, well, now we have to think how many face cards there are. Well, there's king, queen, or jack. All of those cards have faces on them. So we have a king, we have a queen, and we have a jack. And this is for hearts, right? Then for diamonds, we also have a king, a queen, or a jack. Then for, I can't even draw it. For spades, we have a king, a queen, or a jack. Oh my gosh, I didn't realize I was going to try to draw clubs right now. Let's say it's like this. I don't know exactly. I don't remember what it looks like, but it's like that. And we have a king, a queen, or a jack. These are all the face cards because they literally have faces on them. Okay, so how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Or you could think of it like this. There is 4 of every card, and there are 3 different types of face cards, jack, queen, and king. So that means there are 12 cards that are faces out of 52. Let's see, divide by 2, we get 6. Divide by 2, we get 26. Divide by 2, we get 3, 13. So we get 3 out of 13. Okay, so you could be asked any number of card questions. They're pretty straightforward. I like card questions. They're not too bad. But you can always ask me if you're having trouble, or you can even bring up a deck of cards on your computer just to look at it. But yeah, that's how cards will work. And it really makes it nice for us to calculate events in that fashion, or calculate probabilities, I should say. So assuming an equal chance of having a boy or a girl at birth, what is the probability of having 2 girls and 2 boys in a family of 4 children? So now here's the thing. We're going to have 2 children. So we know it's, we're going to have 4 children, and we know there's 2 outcomes per birth. So this would be 16. Okay. So we have 2 to the 4th equals 16. All right. And now what we're looking for is the probability of 2 boys in a family of 2 girls and 2 boys. So 2 boys and 2 girls. Okay. So what we're going to do is we're going to look for all the situations that have an equal amount of boys and girls. So this one's out, this one's out, this one's out, this one's out, and this one's out, right? However, there's girl, girl, boy, boy, there's girl, boy, girl, boy, there's girl, boy, boy, girl, so on and so on and so on. And these are out, and these are out, and these are out. So how many situations? There was 6 out of a total of, we said 16. So this would become 3 out of 8, or 0.3, 75. Okay, that's the decimal version of that. Wait a minute. Did I divide wrong? Divided by 2? Hold on. Let me double check my math. I don't know. Let me double check real quick. Yeah. Assuming equal chance of having boys or girls, what is the probability of having 2 girls and 2 boys in a family of 4 children? So we get 6 out of 16. Okay. Now I think, yeah, I just think so I have my notes. There's a typo in them, I guess, but yeah, that would be the answer, 0.375. 6 out of 16 is 0.375. Okay. So, and you guys could look at this, and they might say, what's the probability of having exactly 1 girl? Well, we look for the situation that has only 1 girl in all the combinations. Okay. Well, that's here, 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 and here. All those situations or all those events only have one girl, okay, or all those outcomes, I should say. So we're going to have 4 out of 16, which is 0.25, okay, or 1/4, okay? So either one of those would work. So you can ask a lot of different ways that we can do this. This is a good little chart for you guys, maybe to keep when you go to take the exam. So if I ask a question about this scenario, you have the sample space right here, and you can just figure out which one you're looking for, okay? So relative frequency, a second way to determine probabilities is to approximate the probability of event A by making many observations and counting the number of times event A occurs. This approach is called the relative frequency method or empirical method. So what it does is it says the number of times, the probability of event A occurring is equal to the number of times A occurred divided by the total number of the observations. Okay, so let's try that here. So it says a fair coin test. If you are interested in only the number of heads when tossing 2 coins, then the possible events are 0 heads, 1 head, or 2 heads. Suppose you repeat 2 coin tosses 100 times and your results are as follows. So again, imagine you actually, and you could actually do this yourself. You could flip a coin, 2 coins 100 times and count the number of heads, okay, that occur on the double coin toss, all right? So they did it, and they said that they got, for 0 heads, they got 22 heads, or I'm sorry, 0 heads occurred 22 times, meaning that they flipped tails twice. 1 head occurred 51 times, and 2 heads occurred 27 times, okay? So let's take this relative frequency. So probability of 0 heads being tossed, well, that would be 22 out of how many observations? 100. So this is 0.22, okay? Probability of 1 head being tossed, they said 51 divided by 100, and this would be 0.51, okay? Probability of 2 heads being tossed would be 27 out of 100, so this would be 0.27, okay? And this would account for the total 100% of every situation, okay, of all these scenarios. So now they say, compare the relative frequency probabilities to the theoretical probabilities. Do you have a reason to suspect the coins are unfair? So now let's think about this. Okay, so we found the relative frequency says that probability of 0 was worth 0.22. Probability of 1 heads was 0.57, I believe, or no, 0.51. And then the probability of 2 would be 0.27, okay? So that's when we did the experiment and we flipped it, we actually got these scenarios or these probabilities. Now let's do what theoretical says, okay? Theoretically speaking, 0 heads, okay? So theoretically speaking, 0 heads, probability of 0 is equal to 0.25, okay? The probability of 1 heads is equal to 2 out of 4, okay? And again, all I'm doing is, remember our coin up here? How many of these, if you look over here at this, how many of these had no heads? 1 of them. So theoretical probability says that we should get 1 out of 4. How many had 2 heads? Or I'm sorry, how many had only 1 head? 2 out of the 4. And then how many of them had both of them heads? Well, that would be, once again, 1 out of 4. If we go back up here and look, this was the only scenario that had 2 heads right there, right? So we're just using like all the theoretical probabilities for each situation. Now this would be 0.25, this would be 0.50, and this would be 0.25. Now let's compare. Let's look at 0.25 compared to the experiment. That's pretty darn close, right? Now let's do 0.50 compared to the experiment. That's pretty good as well. Let's do 0.25 compared to 0.27. That's pretty darn close as well. So I feel that the coin is more than likely fair. So it's not a weighted coin. Somebody didn't cheat or try to, put a little bit of extra weight on one side. So when you flip it, it lands a certain way. you know, or whatever the case may be. I feel like these probabilities theoretically are so close to the relative frequencies that it's probably a legit coin. There's something that we're not going to cover in this class per se, but it's called the law of large numbers, and it says that if you do enough experiments, if you have the event occur enough times, you observe it happening enough times, eventually the theoretical probability or the true probability of the event will show itself. In this case, within 100 tosses, it's pretty close to what it's supposed to be. Now, I think that's why people gamble, is because they're trying to beat the true probabilities or the theoretical probabilities and hit like that little hot streak. But again, that's on a short sample, on a small sample. If you take it over the long sample, the casino is always going to win. That's the whole point of Vegas, is they're always going to win, because the theoretical probabilities and the law of large numbers tells them that eventually the probabilities will come true, will show themselves. So even after 100, it was still pretty good. So we have three approaches to finding probability: a theoretical probability based on the assumption that all outcomes are equally likely. It is determined by dividing the number of ways an event can occur by the total number of possible outcomes. Relative frequency probability based on observation and experiments is relative frequency of the event of interest. And there's this new one, subjective probability, is an estimate based on experience or intuition. You know, for example, the weatherman does subjective probability, or it's almost like an appeal to authority, you know, based on data and, you know, expert knowledge. They give you your probability. I don't like the subjective probability as much. I like to stick to theoretical or relative frequency, but let's just go over a few of these, okay? Let me see how much we have left. Oh, wow, we still have quite a bit left, okay. Okay, so identify the method that resulted in the following statement. So I am 100% certain that you will be happy with this car. Okay, so that's definitely subjective, right? Subjective probability, right? Is an estimate based on experience or intuition. Again, they didn't really give me a lot to go on there, right? So it's definitely not theoretical, and it's definitely not relative frequency. So then the next one says, based on government data, the chance of dying in an automobile accident during a 1 year period is about 1 in 8,000. So they tell you, you know, they've gathered data and basically observed this, right? And then they're telling you it's 1 in 8,000. So this sounds like relative. So this is relative frequency. Okay, let's go to the next one. The probability of rolling a 7 with a 12-sided die is 1 in 12. Okay, so what does that sound like? Does that sound like relative, or does that sound like theoretical? Like they already know what's supposed to happen on the dice or on the die. So I'm going to say that that is theoretical, right? Okay. Everybody good with this? Hopefully. Again, let me know. These are good homework questions. Good, you know, questions that might be on the exam. They're not super hard, but you do have to know what you're talking about. And they're quick hitters, so I can ask you a couple of them and not feel that I'm taking up too much time on the exam. So these are definitely problems you want to look into on the homework as well. Probability of an event not occurring. Okay, so if the probability of event A is probability of A, then the probability of event A does not occur is 1 minus the probability of A. So in a lot of books, this is called probability of A bar or A not. So it's saying not A. What's the probability of not A occurring? So think about it like this. If I told you that the probability of raining tomorrow, and I told you that this is 15%. Oops, not 15%, 0.15. Let's say that's the probability of raining tomorrow. I could follow this up with saying, what is the probability of not raining? Well, you should know that. If it was the probability of raining is 15%, the probability of not raining, so the probability of not raining tomorrow is equal to 1 minus 0.15, which would be 0.85. So that's how you can use this whole not idea. You could also do this probability of raining and then put a bar over it. That means not raining in this particular problem with this particular event of raining. So again, just keep in mind that this one minus thing is basically saying that there's total probability. If the likelihood of an event occurring is between 0 and 1, then the likelihood of the event not occurring is 1 minus whatever that was, okay? So we come back over here, and that's where that's where this 1 minus comes from, right here. 1 minus the probability of A, all right? So it says, since the probability of family of 3 children having 1 girl and 2 boys is 0.375, what is the probability of a family having 3 children not having 1 girl and 2 boys? So that would be probability of not 1 girl, 2 boys. Let me see what they mean by that. So what is the probability of a family of 3 children not having 1 girl and 2 boys? So since the probability of a family of 3 children having 1 girl and 2 boys is so they mean not for this whole thing. This is kind of confusing. I just wanted to reread their question. They kind of mean it like that. Not 1 girl and not 2 boys, okay? So that means that if the family of 3 children having 1 girl and 2 boys is that, well then what would not that be? It would be 1 minus 0.375. So that would be 0.625. Okay, and that's all there is to it. So this idea of not is a very powerful tool that I use when I teach my statistics class as well. And it's just something that makes problems a little bit easier and more convenient. You know, you use it a lot with at least and at most even sometimes, but let me see. I want to see if it's, wait, is that no, there's more, right? Okay. Let me show you something. Okay, so I want to show you guys something real quick that's not in the notes right here. So I'm going to come over here and I'm going to say, okay, so we got this, and I would say find the probability of a family having at least 1 girl in 3 children. Okay, so they're going to have 3 kids. What's the probability that they have at least 1 girl? So this is kind of the hard way to write it. Okay, so probability at least 1 girl. Okay, so what we could do, and again, this is a little bit more complicated, okay, is we could think of all the situations in a family having 3 kids, all of the situations that have 1 girl or more. That's what at least means, right? Is 1 girl or more. Well, luckily for us, we have this chart that they gave us way up here, which makes it much nicer. Okay, so what I'm going to do is I'm going to come up here, and here's a family. Oh, this is, you know what? That's not good enough. That doesn't help because that's for 4. Okay, well, let's do it in a family of 4. Okay, so we can use that chart. 1 girl in 4 children. Let's do 4. I forgot the chart was for 4. Okay, so at least 1 girl. So what I have to do is I have to find and count every situation that there is 1 G. The moment I see a G, I have to count it. So here's 1, here's 2, here's 3, here's 4, here's 5, here's 6, here's 7, here's 8, here's 9, here's 10, here's 11, here's 12, here's 13, here's 14, here's 15, and here is 16, okay? So this is the only one, this bottom one right here is the only one that does not have 1 girl, right? So that means that out of the 16 total probability or 16 total outcomes or possibilities, 15 of them had at least 1 girl out of the 16 total. Okay, so that would be that. But that's because we had that table, we had that chart that told us everything. What if we didn't have that, right? What if I said probability of at least one girl in 3 children. And so now we can't use the chart because that one was for 4. So what we're going to do is we're going to use this idea of not, okay? So now what's the only situation? What's the only situation that does not have a girl in it? So, you know, there's girl, boy, girl, 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 boy, boy, girl, girl, you know, all of those. We'd have to write them all out, and then we'd have to circle all the ones that had at least one girl. So that means if there's 2 girls, we have to take that as a success. If there's 3 girls, we take that as a success. So this situation, the only thing that's not included is 1 minus the probability of not girls, okay? So what's the probability of not girls? Well, that would be boy, boy, boy. That scenario has no girls, okay? It has no girls in that event, okay? Or in that outcome, I should say. So, well, I guess that is the event, and boy, 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 each one of those is the outcome. But needless to say, probability of not girls means what's the only, or what's the situations that don't have girls in it? How many are there? Well, there's actually only 1 out of the 8, and that would be boy, boy, boy. So then that means we have 7 out of 8, which is actually 0.875. So I didn't even need the table because I could use the 1 minus part. So that makes it kind of nice for that one. Probability distribution represents the probabilities of all possible events. To make a probability distribution, do the following: list all the possible outcomes, use a table or figure if it is helpful, identify the outcomes that represent the same event and determine the probability of each event, and make a table listing each event and the probabilities. The sum of the probabilities must equal 1. Okay, well, we're not going to do that in the way that the book shows. I don't like this method. And again, it's the same. How do I say this? What I'm about to do and what the book does are exactly the same thing, but theirs takes up a lot of space. So here's what I would do if you're going to roll 2 6-sided dice. So for 2 6-sided dice. So if you roll 2 6-sided dice at once, here's what I want you guys to do. You just draw this little bar, maybe put this in your notes or something like this for when you take the exam, because if I ask you a dice question, this is going to make it really easy. And then what you do is you just do 1, 2, 3, 4, 5, 6. Oops, I actually did this wrong. It's supposed to be right here. And I can't draw. Okay. So here's the plus, here's 1, here's 2, here's 3, here's 4, here's 5, here's 6. So what I'm going to do is I'm just going to do these little columns here. And I'm going to make little rows here. Okay, so I'm basically doing what your book is doing, but this is just for me, it works better. And so what we're going to do is we're going to take combos of everything, okay? So 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 5, 6, 7. Now we can go the other way. So I'm going to start here this time. 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 5, 1 plus 4 is 5, 6, and 7. So once you start doing enough of these, you see the pattern. You just go 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, 6, 7, 8, 9, 10, 7, 8, 9, 10, 11, 8, 9, 10, 11, 12. So the reason this is nice is because now I can ask you any probability. So this is all for on 2 6-sided dice being rolled. So find the probability of rolling a 7. These are all the different ways that you could roll a 7. So what I'm going to do is I'm going to find, here's my 7, 7, 7. See this diagonal line right here? I'm going to circle all of these guys in red. Those are all the possible ways I can roll a 7. 1, 2, 3, 4, 5, 6. So there is 6 ways out of 6 squared, which is 36. So our sample space has 36 elements in it. So this is 1/6. Now you guys hopefully see that that could go really good then, because now I could say probability of rolling a 5, right? So let's find the number 5. Oops. Let's find the number 5 and let's circle it. How many 5s are there? There's 4. So I'm going to say 4 out of 36, which is 1/9. Not so bad, right? What's the probability of finding a 4 or rolling a 4? Let's go here. Here's 1, 2, 3. So we're going to say 3 out of 36. So this is 1 out of 12. Okay. So these are the probabilities of rolling these numbers on two six-sided dice. And you could do this all day because now you have this nice little setup. Okay. And again, this is the same thing. This table and mine is the same, but they just actually show you all the addition. I just say do it in your head. Okay. So and this is whatever. I think once you have the table, you guys can go ahead and just count the probabilities yourself. But notice they're showing you if you add all of these probabilities up, look what you get. You get 1, which it better be, right? It better be 1 because that was, we just spent the last 30 minutes talking about all probabilities are between 0 and 1 of event occurring. So the most likely event of the sum of 7, which occurs for 6 of the outcomes, the probability of 7 is 6 out of 36 is 1/6. And that's what we got right here. Okay. Odds are a little bit different. Odds are the ratio of the probability that a particular event will occur to the probability that it will not occur. So the odds for an event A are probability of A and probability of not A, okay? And the odds against an event A are probability of not A divided by the probability A. So it just depends if it's the odds for or the odds against, which one you divide, okay? Whenever it's for, well, basically, I don't know if there's an easy way to memorize it, but the odds for always have the probability on top divided by the probability of not A, and the odds against, they just flip-flop. By the way, in gambling, odds are in general against you. They're telling you the odds against you winning, okay? Okay, so what are the odds for getting 2 heads and tossing 2 coins? What are the odds against it? Okay, so we're going to take and we're going to do probability of 2 heads divided by the probability of not 2 heads, right? So this is the odds 4. So this is 4. Okay. Now, the probability of getting 2 heads is 1 divided by 4, right? If we go back to our table, and the probability of not getting 2 heads. Now, how many of our choices, remember there was heads, 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 tails, tails, heads, or tails, tails. How many of those events do not have 2 heads? Well, this one doesn't have 2 heads, this one doesn't have 2 heads, and that one. So there's 3 out of 4. So that means that when we multiply this or divide it, we turn it into the reciprocal, and we get 1/3. Okay, so we get 1/3. All right, so that's the probability for. Now let's go against. So now it's probability of not 2 heads divided by probability of 2 heads. So this would be 3/4 divided by 1/4. So 3/4 times 4/1. So this would be 3, the reciprocal. Okay. So sometimes in gambling, they'll say the probability would be 3-1. So this is how they would write it in gambling, or 3-1. Okay. Not that you guys should go out and gamble, but that's just how it works. Okay. Okay, one more page. Let's just take a look at this. So at a horse race, the odds on Blue Moon are given as 7-2. Okay. If you bet $10 and Blue Moon wins, how much will you gain? Okay. So that basically means you get 7 for every $2 that you spend. Okay. So the odds mean, so this means that for each $2 you put down, you spend, or you bet on Blue Moon, you will gain $7 if you win, right? All right. So if you bet $10 and Blue Moon wins, how much money will you gain? Well, let's see here. How many twos can we fit into $10? So we do 10 divided by 2 and we get 5. So that means that there's 5 $2 in 10. So we're going to take and we're going to multiply 5 times 7, right? Because they said we gain $7. So we would get $35. Okay. So when you go to collect, so when you collect, you get $45. And remember, the reason for this is you won 35, but didn't you also originally put $10 down on the bet? So you get your $10 back. So you actually will get a payout of $45. Now, in reality, you only won 35, but you will get $45 back at the window when you go to bet or receive your bet. Okay, you guys, the video is already longer than I wanted. So if you have any questions, feel free to ask me. But other than that, thanks for watching. That's going to do it for 7A.